Thank you so much for joining us today. My name is Steph Nelson. I'm an application engineer for Siemens. Your other co-presenter is one of our great colleagues from Germany, Olaf Strama. Olaf, would you like to introduce yourself?
Hi, hello. I'm Olaf Stramer. I'm here in Germany, the department from Siemens called Industrial Quality Testing. We are responsible for the Simcenter Analysis product that can be used for noise and vibration-based product quality control.
And we're going to learn a lot more about some of what the ANOVA stuff can do later this presentation. We're going to be talking about Cepstrum today. So if you're not familiar with Cepstrum, this is your day. We're really going to be getting into how it works and the processes behind it. So let's get started. So the first thing I want to point out is Cepstrum is kind of a strange name. The mathematical process, which we will go on to see, is a spectrum of a spectrum. So really what we're doing with a Cepstrum is we're taking an FFT of an FFT, or a fast Fourier transform of a Fourier transform. And because of that, it's got kind of a strange name. People who came up with this thought it would be funny or interesting or cool if they reversed the first few letters of spectrum, because it's a spectrum of a spectrum, and ended up flipping those and you get Cepstrum. So Cepstrum comes from the first couple letters of spectrum inverted. Some more literature terms if you're curious. So Cepstrum is spectrum. Liftering comes from filtering, which is filtering in the Cepstrum domain. Harmonics are harmonics. And Q-frequency, this is the important one, is frequency. This is the units we're going to be dealing with today. So this is just something to keep in mind as we're going along. Now, Cepstrum is really useful for fault detection. We'll go on to see why that is, but typically a lot of people use it for gear and machine analysis. They'll use it for condition monitoring. And then historically, it's been used for earthquake monitoring and voice processing is where mostly Cepstrum had been used. If you're into machine analysis, if you're interested in fault detection or condition monitoring, Cepstrum might be a very good application for your data. So what is the Cepstrum? I mentioned it's a spectrum of a spectrum, but what the actual mathematical process is, which we will be going over, we have some type of time signal. It's going to be transformed into a Fourier transform. Now, Olaf, if I take a time signal and I transform it in a Fourier transform, what am I getting?
You get a signal in frequency domain or more or less a spectrum, usually
Yeah.
a complex spectrum.
Yeah, absolutely. I'm getting a complex frequency spectrum. I've taken my time domain, I'm in the frequency domain. So now that I'm in the frequency domain, what I'm going to do is I'm going to take the log, and we'll explain why that happens in a bit, and then I'm going to take an IFFT. But since I've taken the log of this Fourier transform, and it was a complex spectrum, I've changed what this signal looks like. So now if I do an inverse Fourier transform, I'm not going to get my original time signal. I'm going to get something that looks like this, and this is actually the Cepstrum domain. So I have Q-frequency on my x-axis and amplitude on my y-axis. And for all of you math people out here, this is the equation for a Fourier transform. We are actually going to be covering this because I know that this is very complicated, but I actually think there's a better intuition of what the Cepstrum is doing if we go through how this equation works. So if you've never seen the Fourier transform or how it works, you're really going to get to understand this equation today. Another quick thing to note, the only difference between a Fourier transform and an inverse Fourier transform, which is this green equation here, is the phasor is rotating in the opposite direction. So here I've got a minus j, and then the inverse Fourier transform, I've got a j. And a really important thing is because we've done this inverse Fourier transform here on Fourier data, instead of getting f, we're going to get Q-frequency, which is 1 over f. So all of these values, if I were to look at a Q-frequency plot, all of these peaks are located at 1 over f. Something to just keep in mind as we go forward. So harmonics are fundamentals of a frequency that get excited and can typically, if it's being excited, be heard if it's something in the acoustic space. So for example, if I have a tuning fork and my tuning fork is set to 440 hertz and I whack that tuning fork and it vibrates, what I'm going to hear is 440 hertz. But I'm also going to hear all of the harmonics of 440 hertz up to a certain frequency. So for example, here is a spectrum of a 440 hertz tuning fork. So I have my peak here, and then I have a harmonic at 880, 1320, 1760, and so on and so forth. These are all multiples of my fundamental frequency. These are all harmonics. And the important thing to keep in mind for harmonics is that they are evenly spaced in the frequency domain. Notice how the fundamental and then harmonic 1, harmonic 2, they're all spaced apart by 440 hertz. And that's really the important thing, because what we're going to be doing with the Cepstrum is we're going to be looking for components in the frequency domain that are equally spaced. Because sometimes that's not always obvious when you're looking at a frequency plot, which components are equally spaced and which is just noise. So harmonics are evenly spaced. This is what we will be using Cepstrum for. If you have data that doesn't have equally spaced periodic content, the Cepstrum is not going to work. And there will be a quiz in a little bit, so keep that in the back of your mind. So that Fourier transform that we talked about, most people, if you've heard of the Fourier transform, understand that it takes a complex waveform in the time domain, something like this, and it breaks it apart into a unique combination of sine waves and gives you the result in the frequency domain. But we're going to talk about how you get from here to here using that equation. You put in a time trace and you get out a frequency plot. We call this an FFT. It's pretty synonymous with Fourier transform. It just stands for fast Fourier transform, which is the algorithm used to get from the time domain to the frequency domain. This is how an FFT works. This equation looks really complicated, but I promise you that it is not. So here, what we're doing is we're taking our discrete data points, x of n. So this is if I took a time signal, I have n number of samples, and we're multiplying this data by this complex exponential. Now, if you're not familiar with this complex exponential, this is basically can be broken down into a combination of cosines and sines. And this is, I should say, the imaginary portion is the sine. Cosines and sines. So if you've ever seen the output of an FFT, it gives you the output as a complex value. The complex value is really just how much of the imaginary portion is correlated to a sine wave at that particular frequency, and how much is correlated to a cosine wave. Now, a lot of people think that if you get a complex number out of the FFT, usually something in the form of a plus bi, that the real part is the magnitude and the imaginary part is the phase. And that's actually not true. That's not correct. The real part is the part that correlates to a cosine wave, and the imaginary part is the part that correlates to a sine wave. So if I were to plot the real versus the imaginary, the angle between is the phase, and the magnitude is the vector length. That's just some fun DSP. That's not particularly related to Cepstrum, but it's always fun to explain how that works. Okay, so I'm taking data. I don't know which frequencies it's at, so I'm going to guess at different cosines and sine waves, and I'm going to multiply them together and sum the result. So hopefully it'll be obvious why that this is testing the correlation of each of these different frequencies. And once again, we don't know which frequencies are present, so we're going to guess, we're going to iteratively go through and guess which frequencies are in the signal. So let's do this. I have a signal here, and this is discretely sampled, so I have different points. And spoiler alert, I'm going to tell you it's a 2 hertz sine wave. Let's start guessing different frequencies. So the first thing I'm going to guess is 0 hertz. So the cosine of 0 is 1, and the sine of 0 is 0. I have a 0 cosine wave and a 0 hertz sine wave. And what I can do is I can see really quick right off the bat that if I were to multiply these values by one another, Olaf, let's start with the red one. If I multiply everything by 0 and I sum the result together, what am I going to get?
I guess 0.
Yeah, very good, 0. So I'm going to plot the sine response in red. So 0 is what's going to happen if I multiply all my data values together and then I sum the result. I'll get a 0. Now, if I multiply the cosine by 1, what am I going to get, Olaf? This one's a bit of a trick.
It will be 0 again because you have the same number of points above and below 1, I guess.
Yeah, that's exactly right. It'll be 0 again. And the reason for that is these points, when I sum them together below, will cancel these ones above, and I'll end up with 0. Now let's do a 1 hertz sine wave. You could see right now that if I were to multiply, this point here by this point here, here by here, and sum the result together, these don't really look like they would correlate. And if I sum them together, I'm going to see that I get 0. I could do it again for a cosine wave, and I could really quickly eyeball that the cosine wave doesn't correlate either. Now, how about this, Olaf? Does this look pretty good?
Yeah, that fits quite perfect.
Yeah, and that's because now I'm at 2 hertz. This is a 2 hertz sine wave. I told you earlier that this was a 2 hertz sine wave. So when I multiply these points by one another and I add the result together, I'm going to get a really high value. And I'll actually get a value after I scale it properly at the amplitude of this sine wave. So this is a 3-unit sine wave. I'm going to get 3 units in my frequency spectrum. Now, the cosine wave doesn't have a lot of correlation, and I could keep doing this and doing this for different frequencies, and what I'll end up with is a FFT plot. So now I know that if I were to look at this FFT plot, I have high correlation or a high value at 2 hertz. So this is a 2 hertz signal, and nothing anywhere else. Did that make sense, Olaf?
Yes, sure.
Okay, let's try this for a sawtooth wave. This is how the Cepstrum works. We are applying the exact same principles, but now we're doing it, instead of in the time domain, in the frequency domain. And we're doing it to keep track of where the periodic components are. Sine waves and cosine waves are naturally periodic functions. So if you're looking for periodic components in a signal, a sine wave and a cosine wave is a good way to look for that. Really what we're doing is we're exploiting the FFT in a way that isn't normally used. So here I have a sawtooth wave, and if you had to describe a sawtooth wave in the frequency domain, Olaf, what would you say that it looked like?
Now I have the basic frequency and all the harmonics with a certain level.
Right. So I have my basic frequency at 2 hertz, and then a sawtooth wave is made up of a combination of equally spaced harmonics that happen to be the 2 hertz spacing apart, the fundamental frequency apart. So here's what I'm going to do. This, obviously, isn't how waveforms look in real life, unless you have a magic continuous sampler, but we don't. We have discrete points. So what it really looks like if I were to take samples is something like this. Now, what I'm going to do now is take the log of that, and the reason I'm taking the log is to compress this dynamic range to make these points easier to fit to for the Kestrel algorithm. If there's massive differences between these points, a sine wave isn't going to fit as properly. So we're compressing everything together to make it easier for a sine wave to fit them. Okay, now I can start doing this again. And one thing I'll notice in the frequency domain, a lot of frequencies, if I'm starting at 0 hertz, are 0. So this is actually going to have a high correlation. Now, Olaf, is it super useful to us to know what's going on at 0 hertz in the Cepstrum domain?
In practice, not. Nobody looks at this point because it's more or less the DC component of our logarithmic value, so it has no information.
Yeah, so all Cepstrum graphs will probably have a high zeroed component, and that's just because a lot of the frequencies are at 0 or near 0, so that naturally this is going to fit those lines. Now, we mentioned earlier that frequency, because we're going backwards now, we're doing an IFFT, is inversely proportional to Q-frequency. So in the Q-frequency domain, it's 1 over F, and all of our values are going to be at 1 over F. So we're going to have to think of this a little bit backwards. So now if I try to fit a 1 hertz sine wave, I can just quickly eyeball that none of these are really correlated. None of the points really fit. So I'm going to get 0. Now, if I do something like this, I'll see that some of the points fit. Not all of them, because this isn't a perfect 2 hertz sine wave, correct? This is just happen to be spaced 2 hertz apart. Now, Olaf, if this is 2 hertz in the frequency domain, and I talked about how the Q-frequency domain is 1 over F, where is this going to appear in our Q-frequency graph?
Yeah, you have to think reciproc the other way around, so 1 over 2.
Yeah, exactly. So this is going to appear at 1 over 2. Now, it's not going to be crazy highly correlated because, once again, this is not a perfect 2 hertz sine wave, but we are going to see some correlation because these components are 2 hertz apart. And I could see the same thing with the cosine wave. And I could do this again for the rest of my frequencies, and I'll get something that looks like this. So I'll end up with a peak at my Q frequency of 1/2, and that corresponds to 1 over 2, 2 hertz, the frequency of this sawtooth wave. So if I were looking at this plot just by itself, I would think to myself, okay, at 2 hertz, there are multiple harmonics in my original frequency signal. With a sine wave, we can see how this will work. Here's my points. A sine wave is a single peak, right, Olaf? We don't have any other magic frequencies in a sine wave?
Right.
Yeah, so if I take this away, have my discrete points, I can do a logarithm, and right away you can see that this is pretty much 0. And if I try to fit points, I'll pretty much get 0 across the board. And the reason for that is there's nothing periodic or harmonic or repeating in a sine wave. So there's nothing to fit it to. So my graph for sine waves should probably be pretty flat. Here's a quick review of some common signals. We talked about a sine wave. In the frequency domain, it'll appear as a single peak. And in the Cepstrum domain, it'll appear as nothing. And a sawtooth wave we looked at in the frequency domain is made up of multiple evenly spaced harmonics. In the Cepstrum domain, it'll appear as peaks at 1 over this spacing, 1 over f. That's really what we're looking for in the Cepstrum domain. A square wave has odd harmonics, so we're skipping a harmonic. So in the Q-frequency domain, we're going to have more because it's 1 over f at this spacing. Random kind of looks like a bunch of random white noise in the frequency domain. So Olaf, if you had to guess based on our pattern, what would you get for the Cepstrum of a random signal?
The noise will lead to noise again.
Yeah, we're going to get something that's pretty noisy that doesn't have any high amplitude because there's nothing periodic in here. Here's a quick example of why you would use Cepstrum. I have 2 time traces. One has a gear with a defect, the orange. One has a gear with no defect on the blue. Now, right off the bat, it's kind of hard to tell, just looking at the time signal, where the defect is. So we can bring this into the frequency domain. And if we're looking in the frequency domain, I think it's still pretty complicated to tell where the gear defect is because there's a bunch of noise on this signal. But if we bring this into the Cepstrum domain, we're going to be taking this and we're looking for which parts are harmonic. We can get very easily identifiable peaks. So here, for example, is a gear defect. I see that the blue one with no defect has low amplitude, and the orange one with the defect has high amplitude at a frequency that corresponds to the gear. Now, one quick thing, because Olaf is going to talk about how this is applied in real life. If we have a gear spinning at a constant speed, and we're looking at the frequency, and we're doing an analysis, it'll appear here in the frequency domain, but if it's changing speed even a little bit, it's going a little fast or a little slow, it won't appear as a single peak because the frequency of the speed is changing. We'll end up with multiple peaks, so it kind of ends up with a smearing effect in the frequency domain. And this can be a problem for the Cepstrum algorithm, because if you're trying to measure where those periodic components are and everything's smeared, well, you're just really not going to get good results. If we were to do something called synchronous sampling, which you may have heard of, this is where we track a gear based not on its frequency of its spinning, but based on the number of rotations. And we call this the order domain. So an order of a consistent spinning gear will be a single line. And if the gear is changing, it will also appear as a single line because we're tracking how many times it's rotating, not necessarily the speed at which it's rotating. So if we were to perform a Cepstrum analysis on this or in this domain, we will get a much cleaner answer than if we had a gear that was increasing and decreasing speed even just a little bit in the frequency domain. So if you're going to do sampling and perform Cepstrum on gear analysis, we really recommend you do synchronous sampling. And then just to show, this is a gear spinning at a consistent speed and a gear spinning at a changing speed over time. My last thing before I turn it over to Olaf, because I don't want to talk too much, some of these are mathematically related by interesting ways. The time domain, the frequency domain, and the Cepstrum domain. If you remember, you might have heard before that convolution in the time domain, taking 2 signals and convolving them by one another, is actually equal to multiplication in the frequency domain. These are mathematically equivalent. But fun fact, because we took the logarithm and we transformed it back into the Q-frequency domain, the Q-frequency domain is actually equivalent to the addition or subtraction of 2 signals. So sometimes people will actually use the Cepstrum domain to subtract or add out different path characteristics in their signal. And this is actually employed a lot in voice measurements and voice processing. So just something cool. Convolution in the time equal to multiplication in the frequency, which is equal to addition in the Cepstrum domain. And the units in the time domain are seconds, minutes, hours, days, however you want to measure time. In frequency, it's usually hertz or radians per second. And in Q-frequency, it's usually 1 over the frequency or 1 over the order. Okay, Olaf, are you ready to take over?
Yes. Now let's switch over to practice, to the real life, the real world in the shop floor. That's what we are doing with our sophisticated signal processing functions. We try to identify the root causes of noise and vibration relevant quality issues. We are here talking about a 100% end-of-line test, for example, of electric drive units as they are used in electric cars today. And now imagine what happens if a tooth gear was damaged during the production of such an e-axle and nobody noticed this because everybody made everything right, everybody mounted the stuff in the right way together, but at the end there's a fault inside and nobody knows that there's inside. If something like that happens, it can get expensive. Faulty aggregates are delivered to the car plant, and in the case of serial defect, really high costs can occur. So imagine you made a handling fault in the production line and not only one tooth gear is damaged, but hundreds of them, then it could happen that the complete production of a day is damaged, and this really leads to a lot of troubles. But it's possible to avoid this by a suitable method at the end of line test to find that such kind of faults, even if they appear the first time. And that's what we are doing with our Simcenter Novice. Our approach is based on signal processing. So Steph told before, we have something that rotates in our electric drive units. Therefore, we synchronize on the rotation, and the typical analysis that we do here is an order analysis. So this is our basic analysis. We synchronize on the speed of the unit so that we can distinguish between signals that are synchronous to the speed, that may have their origin in the device under test, and other signal components that are not synchronous. And basically, the non-synchronous signal components are the vibrations, the sound that's coming from the surrounding. Remember, we are in the shop floor, we are on the production line. There are no ideal conditions for noise and vibration measurements. We do not have an anechoic chamber or something like that. We hear all the forklifters. We see all the vibrations of the production line in our data, and we have to separate them from the data that comes from the device under test. An order analysis is a perfect first step on this. Then we calculate the right curve. As Steph told you before, there are some signal types that are very good visible or analyzable in spectrum domain, others are not. And so we choose the right method here to extract the signals of a certain issue from the complete signal. If we talk about something that is harmonic or that has some modulation or some single frequencies, you've seen before that the single frequencies does not show up in the Cepstrum, but very nice in the spectrum. Therefore, we use the spectrum there. Other things like signals with a lot of harmonics are not so easy to identify in the spectrum. Therefore, we use the Cepstrum. And this, as a next step, we go one step further. Then we calculate from the curve a so-called metric. And the metric is a simple single value that helps you to identify a fault. If this value is inside of a limit, then we do not have this kind of issue, this kind of fault. If it's outside of the limit, it identifies that something from this unit, and especially a certain type of fault happens. So that's the complete measurement chain, and it helps to identify typical phenomena that we can have at transmissions or electric drive units. If you look at the tooth gears, ghost orders and gear whine are things that we have to talk about. Gear whine simply happens if the shape of the teeth of a tooth gear are not inside of the tolerances, then the noise emitted or the vibration emitted from the tooth gears are higher than usually, and we hear a kind of gear whine. That's not only a comfort criterion, it also shows us that the shape of the teeth are not right, and that this may lead to a damage after some 100,000 miles. And ghost orders happen if the machining was not made in the right way. Typically, if a grinding machine starts to vibrate, starts to get into resonance in the production of the parts, then structures on the surface occur, and these structures lead to orders that we do not know in advance. Those are the so-called ghost orders. So those are things that described as that lead to harmonic signals with basic frequency only, with some harmonics only, or to modulations. And then we have tooth defects. They can happen everywhere in the production line, during handling of the tooth gears, during the assembly. Sometimes a part falls down and they mount in the unit. At the end, several reasons can lead to tooth defects. And of course, it's very important to detect them. And not only tooth defects are of interest, also damages of bearings. Ball bearing, for example, has rotating elements. If they have a defect, something similar happens than if you have a tooth defect from the signal processing point of view. So the difference between gear whine, ghost orders, and tooth defects is that tooth defects produce transients. They produce ticks. It makes tick, 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 tick every time the defect gets into the tooth mesh. The same mechanism we have for ball bearings, and this leads to a signal that does not only have a basic frequency, but a lot of harmonics. And the distance between the harmonics is the one divided by the distance of the peaks in time domain. Or an angle domain, if you have one peak per revolution, then the distance of the peaks in the order spectrum is one order, and so you have a lot of peaks, and that makes it not so easy to identify them in the spectrum. Okay, let's have a look at the practices now. This is an order spectrum of a gear pair with 13 and 73 teeth. We synchronize on the pinion, on the small tooth gear with the 13 teeth. And what you see here is an averaged order spectrum. This is from practice, therefore it has a lot of noise coming from the shop floor, from the conveyors, and from everything that moves in the production line. And what you see here is not only one curve, you see here a bunch of curves. The blue curves are normal measurements from the production line, which are basically items without fault. And the red line is an item that has a certain fault that we want to detect. And what we see here are the gear mesh orders and the harmonics. We synchronize on the pinion, which has 13 teeth, and therefore we will see a gear mesh order at the order 13. And since this is not a sine wave, but a wave that has a certain different shape, we see harmonics. We see order number 26, order number 39, and so on. Yeah, but you see here, this is not a decent line. You see some other lines around it. What you see here is a kind of modulation. Steph mentioned it in one of her slides, that the modulation is a multiplication in time domain, or in this case, an angle domain. That means you have a carrier, which is in our case the gear mesh frequency, and you have a signal that is modulated on it, which may lead to a defect. And this is a multiplication in angle domain, but in order domain, multiplication will transform to a convolution. And if you convolute something with a sine wave or with a single peak in the spectrum, then you simply shift the other signal around this peak. So let's have a deeper look inside. Okay, let's zoom into the spectrum. We see here two sideband lines, and the distance is, in our case, 0.178, which is exactly 33 divided by 13. So what we see here, we have one pair of sideband lines, and these sideband lines have a distance that leads us to the gear with the 73 teeth. And since we only see one sideband lines, this is a machining error. Perhaps this part is eccentric. So that's quite something where we can build a nice metric from, so that we can distinguish between a defect on the pinion and on the gear by simply looking at the sideband levels, or a so-called sideband energy measure. So we can identify what tooth gear is out of order. And if we do it in a production line, we, of course, will calculate some measure that tells us if this metric is reliable or not. We call this CPK value. If this value is above 1.6, we can say that we can use this metric in the production line with a high reliability. And that's the case in this example. Yeah, and then we have the tooth defect. The same again, we see a spectrum, averaged order spectrum. It's the same calculation than we had before, synchronized on the pinion again with the 13 teeth. And what we see here, the gear mesh orders are visible too. Yes, this one, this one, this one, this one. But there's no big difference between good and bad. That means it does not allow a clear separation. What we see here are pulse trains in parts of the spectrum, but even these pulse trains have a quite small distance to the production. So we see here one peak, another peak, another peak, another peak, another peak, another peak. The orange lines are from one defective part and the red lines from the others. And we see also a pulse train from the red lines. So now we see in the spectrum, there's no big difference. The energy is spread over many lines in the spectrum. So what could help? What kind of analysis? Let's do a Cepstrum. Or before we do a Cepstrum, we have a look in the angle domain. So what we have here is order domain. So let's have a look at the angle domain. There we, of course, can synchronize once on gear pair with the 13 teeth, and then calculate another curve where we look at the gear with the 73 teeth, and we see one peak in one picture, another peak in the other picture. So we can use those two analysis, those two angles, synchronous, averaged, and enveloped, to identify defects on both of the tooth gears. So it would be easy to identify them even with a good CPK value. What is the disadvantage of it? The disadvantage would be we will in a real electric drive unit, for example, we would need to calculate a lot of these pictures. We have to set a lot of limits. And one big disadvantage is if we want to find bearing defects, then we have to take the slip of the bearing into account. So the bearing never is completely hard synchronized to the speed that you measure from the device under test, because it's not a mechanical system that is mechanically locked to each other. So we have slip. And because of the slip, the frequencies are never at the point where you expect them. They are always a little bit beside that. And if you do a synchronization that is not perfect, then the things happen that Steph showed you before. You have a smearing in the spectrum, and you also have a smearing here in the synchronous signal. And if you try to average this, it will disappear. So therefore, let's give the Cepstrum a try. So what you see here is an order Cepstrum. Of course, we take the order spectrum as a basis, and this again is synchronized on the pinion with the 13 teeth. And we see here with a distance of 1 divided by order, the peaks from the orange example. And we see at a point which is again 1 divided by 0.178, which shows us exactly the origin as the gear. Here we are able to distinguish the quite single lines, or only a handful of lines that are affected by a certain defect. So if you look back at the order spectrum, then, for example, the energy that is now concentrated on those two lines was spread over many, many lines. But if you look at those two lines, we are really able to calculate a metric with a high reliability that we can use in the production line. So we could put single assessment metrics on the lines that we already know. And if we look for unknown defects, we can simply put a tolerance curve over the graph and see if something is sticking out, and then try to analyze where this comes from. And this is basically the way how many of our customers work if they have quite complex items like automatic gearboxes with a lot of tooth gears in and a lot of bearings in. Then they even do not start to build a lot of metrics. They simply use a tolerance scheme, or use a tolerance scheme automatically generated by our chameleon algorithm. And if the first time something sticks out, they recalculate where this peak comes from, and then they can identify this peak. And if it happens the next time, they know in advance what it is. So the system becomes more and more intelligent over time, depending from the faults that occur. The blue lines are lines from the production line. That means in the production line, we do not look at absolute values. We always compare the vibration behavior of the item with the normal production. That means to define a metric, we take 50, 100 measurements from the line and compare them with the faulty part. And that's basically also what Chameleon does. So the blue lines are okay items from the production line. The orange lines is one type of defect, and the red line is another type of defect that we did not know in advance. But looking at the 1 divided by orders where we see the peaks, we can assess which of the both tooth gears is defect. Yes, and those are some metrics that we calculate from known faults. And as you see here from the Cepstrum, we can calculate metrics again that show a high repeatability or high reliability so that we can use them in the production line. Setting this up in Novus is quite straightforward. You can set up Cepstra in the same way than Spectra using the Flowlet Spectrum Averaging Basic or Spectrum Averaging. For the practice, I would use the type linear as absolute, because the real Cepstrum has positive and negative values. What you see here is always a so-called absolute Cepstrum. That means we flip the negative values up, so that will be easier to set up limits there. You do not have to set limits in the negative and positive domain. They are always positive. And if something is too high, then it's bad. So that's why it's best practice to use the linear as absolute scaling. Yeah, and if we have effects that only occur in a certain part of the spectrum, then we also can use a so-called zoom Cepstrum. That means here we can concentrate on the range of the spectrum where we have pulse trains and can analyze them to get a better signal-to-noise ratio of our output. Yeah, for the metrics, we have special flowlet that is called order Cepstrum ratio or frequency Cepstrum ratio. So we do this both in order and frequency domain, but 99% of all applications are in order domain, of course. Also here, choose linear as absolute, and you can use a zoom if you know in advance where you have to look at in the spectrum. And here you also can set minimum, maximum limits so that we can define metrics quite conveniently. Yeah, that's it, what I wanted to show you from practice. So you see, with Anovis, we can put this high sophisticated signal processing stuff that Steph explained you into praxis. And it can really help you to save time and costs by detecting defects in the production line.